Hello everybody, Math Hobo here, and today we will be talking about measures. But before we get into that, we'll need to clarify, exactly what a measure is. So let's say that we have an interval, open or closed, in this case open, with endpoints a and b. If we want to talk about the measure of this interval a comma b, then it's measure mu of a comma b is equal to b minus a. And mu is simply the function which extracts a measure from a certain interval. So the length of this interval is simply b minus a. That's very intuitive and understandable. But let's attack a more complicated problem, which is on the real number line. Let's take the endpoints -1 and 1, and let's try to calculate the measure of all the rationals in between -1 and 1. So that would look like Q intersect -1, 1, and the measure of this entire set. So you're trying to calculate the sum of the lengths of each tiny rational number between -1 and 1. And interestingly, this turns out to be 0, and I'll discuss why in a different video, which will follow soon. But what we need to do now is talk about the properties of our measure and define some properties and some restrictions on our concept of a measure. So first property is quite simple. Mu is a function which outputs measure. And measure in measure for us is defined is length, area, volume, and any other higher dimensional relative of these three that exists. So now that's our first property, and our second property is where is our measure defined. So if we take our real number line and we take intervals on our real number line, or sets of intervals on our real number line, we want to be able to attach a measure to each of those intervals, or each set of intervals, or each collection. So what we'll need to do is define the set of all collections of intervals on our real number line. And this is denoted curly P of R, which is called our power set of reals. And what a power set is, let's say power set of set A, where A is equal to the set which contains elements A, B, and C, then you're taking all the set of all subsets which you can create from set A, which will be A. I'm not going to write the set notation for each one of these. A, B, C, A, B, A, C, B, C, A, B, C, and finally our empty set, which is null. And so the collection, the set which contains all of these elements is the power set of A. So now that we've clarified exactly what a power set is, we're going to declare that mu is defined on the power set of reals. So we can take every collection of intervals, and we can take power set of reals, and mu maps power set of reals to the interval 0, infinity inclusive. And this is our input, and this is our out. And this makes sense because it's simply length. And length cannot be negative, but length can definitely be infinite for certain cases. So that makes sense. And number 3 is a more interesting property. It's called countable additivity. And it says if we take, let's say 3 in this case, but any number of intervals, and I'll enumerate them A1, A2, and A3, then if I take the measure of the union over I, AI, if I take the measure of the union of all of these intervals, then that should equal the sum over I of the measure of each of those intervals. So that's saying that if you take all 3 of these and merge them into one single interval, and into one single set, and calculate the measure on that set, then that's equivalent to taking the measure of A1, the measure of A2, and the measure of A3, and summing them all up. And again, that's called countable additivity. Now for our 4th property, which is called translation invariance, it says that if you take some set, or some interval A, with endpoints small a, small b, and if I add to A some constant number k, then the measure of A plus k must equal the measure of our original interval A. And algebraically it looks kind of abstract and tough to comprehend, but if we represent it in diagram, it becomes much easier. So what this A plus k means is that we take our interval A and we simply shift it along in the real number line k units. So we can take our endpoints A and B, shift them along k units, and then so our original measure of A is simply B minus A, and our measure of A plus k is going to be B plus k minus A plus k, and the k's cancel out, and again you get B minus A. So this says basically that if you apply a translation to any interval, the measure of that translated interval and the original interval must remain the same. Now, what's interesting is that there's no function mu, there's no measure function, which satisfies all 4 of these conditions. And in just a moment, I will prove to you why. So let's say that we have an equivalence relation, and we say that x is equivalent to y, not if x equals y, but x is equivalent to y if and only if x minus y is rational. So what this is saying is, let's take some examples. Let's say that x is equal to 5 and that y is equal to 1. Then 5 minus 1 is equal to 4, which is most definitely a rational number. And now let's say we have x is equal to 1 plus root 2 and y is equal to root 2. Then the difference of these two is simply 1, which is also a rational number. However, if we take pi for x, and if we take 1 for y, pi minus 1 is approximately 2.14 something, but it is most definitely not a rational number. So we say now that pi and 1 are not equivalent. However, the quantities 1 plus root 2 and root 2 are equivalent, and 5 and 1 are equivalent. So now we can segregate all our numbers into equivalence classes. So the set of all rationals will be denoted alpha, the set of all irrationals will be denoted beta, the set of transcendentals will be gamma, and so on and so forth. And there will be infinitely many such equivalence classes. And now let's say that we take a representative from each equivalence class. Since each equivalence class is so large, there are infinitely many of each one. So let's select a single candidate from each one, and A, B, C, and infinitely many of those, and let's take each of these representatives and merge them into a set, which we will call omega. And omega, we put a certain condition on, where we say omega goes from in between 0 and 1. So omega is the set of all representatives of each equivalence class defined over tilde, such that each representative falls somewhere in between the interval 0, 1 inclusive. So now that we've defined omega, we will define omega I is equal to omega plus the ith rational number. This quantity qi is the ith rational number, so it could be half, third, fourth, anything. And because rationals are countable, it allows me to enumerate the rationals in this fashion. So if we think about what this is really saying, it's saying that omega I is simply a translation, of our original set omega, qi units away. So we know that omega I is simply a translation. Now, if we remember correctly, we said that omega is an element of 0 and 1. And, oh, I'm sorry, I forgot to mention that this qi, the ith rational number is going to fall in between -1 and 1. So I'm restricting my set of rational numbers, qi, to all the rational numbers in between -1 and 1. So qi will be the ith rational number in between -1 and 1. Now, because we have omega restricted over 0 and 1, and qi restricted over -1 and 1, then if we take the extreme cases, then -1 plus 0 is -1, so omega I is an element of -1, comma, and then 1 plus 1 is 2. So omega I is an element of the set -1 to 2 inclusive. And now, what is the measure of this set? Well, it's just 2 minus -1, which is 3. So the measure of omega I is 3. Now, omega I was simply defined as omega plus qi. So the measure of omega I is equal to the measure of omega plus qi, and omega plus qi is simply the union over I of omega plus qi. So this is equivalent to that. And if we remember, this union here allows us to do something. It allows us to employ the property of countable additivity, which says that this is then equivalent to sigma over I mu of omega plus qi. And now we can employ another property, which is that of translation invariance. And what translation invariance says, if you remember, is that if I take a set omega and I translate it with some constant number, then the measure of omega must equal the measure of this translation. So this really evaluates to sigma over I mu omega. And this is I to infinity union I to infinity, because they're infinite rationals in between -1 and 1. And so now I have sigma I to infinity mu of omega is equal to 3, because mu of our original omega I was equal to 3. But if you think about it, there's no number other than 0 for which this sigma quantity is equal to anything less than infinity. And there's no number, absolutely, for which sigma from I to infinity of any number is equal to 3. So therefore, there can be no quantity mu of omega such that sigma from I is equal to from I to infinity of mu omega is equal to 3. Therefore, there cannot be any function mu which satisfies all of those properties. Thank you.